Hello and welcome to some integration practice for Calculus BC. Let's go right into it. So for number 8, we're given this integral right here from negative 4 to 4 of the square root of 16 minus x squared dx, and we're asked to evaluate this, or find the area under the curve. So let's find out what this curve might look like. First of all, we can say that y equals the square root of 16 minus x squared. We can go ahead and square both sides, and we get this equation right here. And if we go ahead and rearrange that, we'll get x squared plus y squared equals 16. And that right there is just a formula for a circle with the center at the origin. So to find out the radius of the circle, we just take the square root of 16 and we get that r equals 4. So now we know that our graph is a circle with a center at the origin and a radius of 4. So to see a graph of our curve, this is what it looks like right here. If you're wondering why it's only a semicircle and not the full circle, well, if we go back to our original equation, it was a square root function, meaning only positive values can come out of this function, so only positive values are curved. So all the negative half of the circle, it's imaginary numbers, doesn't exist. So now to find the area of this section right here, it's just a simple geometric formula for a semicircle, or pi r squared over 2. Since we know that our radius is 4, we can go ahead and plug that right in, and we get 16 pi over 2, or 8 pi for our final area. And just a side note, you don't need all this work to be able to solve this integral. I just put it here for a visual demonstration. So for number 9, we're given this integral right here, and we know that it equals 24. And we're asked to find the integral from 4 to 2 of k of t dt. So right here, I'm just restating the original integral given in the problem. So we know that this equals 24. So first I'm going to go ahead and split this up into two parts. So this can be split up into these two parts, the integral from 2 to 4 of 6k of t dt plus the integral from 2 to 4 of 3 dt. And then we can set those equal to 24 since we know that the original one was equal to 24 too. And this integral right here, 3 dt from 2 to 4, that can be solved pretty easily. If you're a cool kid, you'll just solve it as a rectangular formula because this line is y equals 3 right here. From 2 to 4, we can say that this area right here is just length times width, or 3 times 2, which is 6. So I'm going to go ahead and plug that in right here. I'm going to plug in 6 for this integral right here. And I have the integral from 2 to 4 of 6k of t dt plus 6 equals 24. So now I'm going to go ahead and subtract 6 from both sides. I'm going to get this. And now to solve for k of t by itself, I'm going to pull the 6 out of the integral. So I have 6 times the integral from 2 to 4 of k of t dt equals 18. Solve for just the integral, and I get the integral from 2 to 4 of kt dt is equal to 3. But if you remember the original problem, it wanted the integral from 4 to 2. And right here we have the integral from 2 to 4. So to find the integral from 4 to 2, we would just take the negative integral from 2 to 4, or negative 3, and that's our final answer. So number 10 was a true or false question. We were given that h double prime of x is continuous on the closed interval 3 to 8, and we want to know if this statement is either true or false, that the integral from 3 to 8 of h double prime of x dx is equal to negative h prime of 3 plus h prime of 8. So this right here is basically just a statement of the fundamental theorem of calculus. And if we want to look at that, this is what the fundamental theorem of calculus states, that the integral from a to b of f prime of x dx equals f of b minus f of a. So we're going to go ahead and see if this fundamental theorem applies to the equation that we were given. So the integral from 3 to 8 of h prime of double prime of x dx should, by the fundamental theorem of calculus, equal h prime of 8 minus h prime of 3. If we go ahead and arrange that, we can get that the integral from 3 to 8 of h double prime of x dx equals the negative h prime of 3 plus h prime of 8. And if we look, that's exactly what was stated in the original question. So this is, in fact, a true statement. Number 11 is another true-false question. We're given this integral right here from negative 2 to 1 of 2 over x cubed dx, and we want to know if it does, in fact, equal negative 3/4. So this looks like just a simple integration problem. I'm going to go ahead and pull the 2 out of the integral and also move the x cubed to the numerator. So I'm going to get 2 times the integral from negative 2 to 1 of x to the negative 3 dx. And this is just a simple power rule integration. So I'm going to get 2 times negative x to the negative 2 over 2 from negative 2 to 1. So I'm going to go ahead and simplify this. I'm going to cancel out the 2's, bring out the negative, and also move x to the negative 2 into the denominator. And what I end up getting is that this equals negative 1 over x squared evaluated from negative 2 to 1. So we go ahead and plug in negative 2 and 1. We get negative 1 over 1 squared minus 1 over 2 squared. And that does equal negative 3/4. So this is in fact a true statement. Whoops, gonna have to hold the horses on that last one because it's in fact not true. If you're wondering why it's not true, well, if we look at a graph of our equation, or we just look at the equation itself, there's clearly a vertical asymptote at x equals 0 because x cubed is in the denominator of the original function. So plugging in 0 would give you a 0 in the denominator, which is a vertical asymptote. So this equation is actually not integrable because of the vertical asymptote at x equals 0. And because it's at x equals 0, we can't ignore it because 0 falls between our bounds of negative 2 and 1. So we can't actually integrate this, and the original statement that said it equals negative 3/4, that statement is false if we can't integrate it. So number 12 is asking us to discuss the difference between a definite and an indefinite integral. So if we look at this chart I made right here, you have an indefinite integrals on both sides. And these are the general forms of both. So for an indefinite integral, a key difference is that it has no bounds. There's no upper and lower bound, whereas a definite integral, there are upper and lower bounds. And an indefinite integral has this plus c right here that a definite integral does not have. So a definition for both of these, an indefinite integral is defined as a family of antiderivatives, whereas a definite integral is defined as the area between the curve and the x-axis between points A and B being the upper and lower bounds. So to see what this looks like graphically, this is what an indefinite integral is. So the shift up is because of that plus c. The c can be any number and the graph will shift up or down that number of units, but it will maintain its shape and form. And these are all just different possible variations of what this function could look like with a different c value. But a definite integral, it's actually the value of that area between the curve and the axis between these 2 points. So clearly these have a big difference. This is giving you an actual area, and this is giving you a set of functions that could describe the area. For number 13, we're asked to discuss the parts that make up this expression right here. So if we remember what an integral actually is, we can remember that it's almost like summing up an infinite number of rectangles between the curve and the axis to get the area. So if we look at each part and its purpose, the first part would be f of x. F of x right here, I have it bracketed. It acts like the function value or the rectangle height. It acts like the height of the rectangles that we're going to use to approximate our curve. D of x, I have it bracketed down there. It's going to act like the rectangle width. So here we have f of x equal the rectangle height and d of x, which equals the rectangle width. So to find the area of a rectangle, we're going to do length times width, height times width, and we'll get f of x dx. That's going to be our rectangle area. So the area of one of these rectangles is f of x dx. So now we have the entire composite function, the integral from a to b of f of x dx. And what that means, it's the sum of the areas of the infinite number of rectangles. So we have all these infinite number of rectangles, and we have f of x dx, which is the area. And because we have this integral sign, we are summing up all the number of the indefinite integrals, or the infinite rectangles between the curve and the x-axis. Number 14, we're asked to discuss the difference between the first and second fundamental theorems of calculus. So here again, I have another chart made. This is the general form for the first fundamental theorem of calculus. You have the integral from a to b of f of x dx equals capital F of b minus capital F of a. Notice how this goes from lowercase f to capital F. Whereas the second fundamental theorem of calculus states that the derivative with respect to x of the integral from a to x of f of t dt is going to equal f of x. Notice how these are both lowercase f's. So in definition, The fundamental theorem of calculus states that the area between the curve and the x-axis between these points A and B, the upper and lower bound, it's going to equal the antiderivative, which is this capital F right here. That's the antiderivative evaluated at the endpoints, again, B and A. Whereas the second fundamental theorem of calculus states that the derivative and the integral, they're going to cancel out. So because we have this derivative and we have this integral, they're going to cancel out. This f is going to remain f and not become the antiderivative. But since we're taking the derivative with respect to x, this f of t becomes the f of x because of the variable. So there's the two fundamental theorems of calculus. And for number 15, we're asked to discuss the calculus and geometry behind the average value of a function. So let's say we have this function, f of x, that's continuous on the closed interval from a to b. We know that the area between f of x and the x-axis between the points a and b is going to just be the integral from a to b of f of x dx. That's just the fundamental theorem of calculus. So we can say that there's some point c on the closed interval a to b where f of c is going to act like a rectangle height, and then naturally b minus a is going to act like a rectangle width. So this is a graphic of what that might look like. So you have the point c on the interval a to b, and f of c is acting like the height of this rectangle, and b minus a is acting like the width of this rectangle. So the area of this rectangle is just f of c times b minus a. It's just the height times the width. But like we stated earlier, the area also equals this integral right here. It also equals the integral from a to b of f of x dx. So if we know that this area is equal to that area, we can set the equations equal to one another. And we can say that the integral from a to b of f of x dx equals f of c times b minus a. So just to make it simpler, we're going to rearrange this and bring the b minus a over to this side. And we get that the f of c equals 1 over b minus a times the integral from a to b of f of x dx. And that's the average value right there. Thanks for watching. Some things about me: I like to run, so I do cross country and track. I also enjoy playing basketball, and I love tourism and traveling.